Okay, great. Why don't we go ahead and get started? We're starting to see a number of people on the webinar, which is great. I'd like to go ahead and introduce our speakers for the December ECSS Symposium, and also thank both of these speakers for fitting in these presentations in what can be kind of a busy time of year, so I really appreciate that. Our first speaker today is Nick Nystrom from the Pittsburgh Supercomputing Center. And Nick is the PI on Bridges, which is one of the newer systems arriving in Exceed land come January. Bridges is really unique in that it combines a lot of different compute capabilities, from high memory to web hosting to database hosting to GPUs, support for things like Spark and Hadoop. So we're, I think, all really looking forward to the kind of novel uses that we're going to see of this system. And so Nick, who's got the most expertise as the PI on the project, is going to tell us all a little bit about Bridges. So Nick, why don't you take it away?
Okay, thank you, Nancy. So I'm going to go fairly fast over today's presentation. I think a lot of people on the call are at least passingly familiar with what Bridges is. So it's somewhat of a review, somewhat of an update, and if there are any questions, I'll try to leave time at the end for them. So Bridges was positioned by the solicitation from NSF for really reaching out to non-traditional users of HPC. And by that, we really mean both people from fields who have never used HPC before, that's folks like the digital humanities, business, to some degree, social sciences, even a lot of computer scientists. But it also means non-traditional ways of using HPC for traditional fields like the natural sciences. So people who are doing things like applying machine learning to problems in material science, for example. And so we set out to build an architecture to be really uniquely flexible and that could accommodate this very broad range of uses. So slide 2, please, or do I have control of that?
You've got control, Nick.
Amazing. Amazing. It works. So Bridges was available, it was made available through an NSF acquisition. It's a $9.65 million acquisition with, as usual, a separate supplement for operations and management. We titled the proposal From Communities and Data to Workflows and Insight, because that's where we really see it. It's really coming from the research communities and what can people do with bright ideas. They are really the limiting factor to leverage data and data across different fields, putting that together in ways that go beyond just single applications in most cases to really get insight out of that. Hewlett-Packard Enterprise is delivering the compute nodes of Bridges. And the disclaimer here is that there's a technical refresh to Bridges that we're doing next summer. And so even though I don't talk about those details, we're still nailing down a few of these things. Everyone knows how technology goes. Okay, advancing to slide 3. Bridges will, as planned, it will be a resource on Exceed. It is being allocated through Exceed. We had the first round of proposals reviewed last weekend. We also have opened the application for startup proposals. And those are coming in. We're reviewing those. And the point of the startup proposals being available even before Bridges is that we have other systems on which we can make people early users. And we also have Bridges hardware installed and running right now. And that will also be available extremely soon for early users. And so by having the startup proposals active early, we get a better sense for who the people are, what they want to do, and who would be eligible for the hardware as we bring it up. We see Bridges is operating with Exceed, with campuses. There's a campus bridging project we have with Temple University. That's a pilot project. I expect that to reach out to other universities also. And it will interface with all sorts of instruments. And so the 3 of those we've represented on this slide just for a feel. The first, I think, is actually probably the most important, and that's just the internet. because the number of people who are working with internet-based data from social networks, from other large data collections or accessed remotely. But we also have interaction with instruments in the classical sense, like high-throughput genome sequencers, electron microscopes, telescopes, and various others. We're also working closely with other NSF ACI data projects, like DIBS projects and others. Certainly we'll be integrating with Exceed resources too, such as Comet, Wrangler, Stampede, and whatever else comes along. Slide 4, I really like to think about an architecture like Bridges in terms of what we built it for, because there's a lot of technology out there. There are a lot of things that one could imagine one could put in a machine, but the question is, what are they good for? And so we really started this by saying, what problems do we want to solve? And then combining technologies to make that possible. So on the left-hand column are just a set of high-level use cases. And these span a number of themes. Many of them are research areas that haven't used HPC. That's particularly for things like we mentioned, like the humanities, like people doing causal discovery. These are people from a philosophy department. And they're going to be leveraging things like gateways. And gateways are going to let people who haven't used HPC use Bridges just as they use Gordon and Comet and other Exceed resources, without having to become experts in HPC, without having to learn programming in that sense. In many cases, even without having to write proposals, they'll just have to be able to get to the gateway, and the gateway owner will manage the community allocation. We're also seeing people who are coupling applications in novel ways into workflows, and particularly for bioinformatics. In many cases, those involve more of these non-traditional elements, like machine learning, and adding to what people have traditionally done, just coupling, say, sequence alignment and annotation, but now looking toward machine learning to help identify genes that are implicated in various pathways and so on. And we're also, in many cases, leveraging large memory nodes and or very high bandwidth within one of the islands and bridges. We'll talk more about what that means, to do things like parameter sweeps and optimizations, and things that very much need HPC resources, but in many cases don't need to be scale out capability resources like you would run on Stampede. So it's complementary to that. I'm going to skip slide 5. This is just potential applications. I think since we're all ECSS here, we understand the breadth of applications that hit ECSS. Many of you have seen the sorts of proposals that came into the recent extract meeting. And I would say at Bridges, many of the ones that explicitly requested Bridges are from these new fields, the vast majority, in fact. Another thing we see is that about a quarter of the proposals coming in had requested ECSS support. And so that is unusually high as a percentage. It reflects these new communities do need a little help getting started. And I expect that to stabilize over time as they get software frameworks, environments are good for them, as gateways are stood up, and as they develop a culture of HPC. So our objectives and approach were really to reach out to new communities, to bring HPC to big data. That was really a theme at SC15. And in fact, I had given some talks there, and the Converging Big Data and HPC panel really resonated with this. Randy Bryant, in fact, came by our booth on Monday night and was interested to learn how much Bridges is addressing the kinds of things he said we need in his panel speech. We're leveraging large shared memory, and that's because at PSC, with Blacklight and even before, we really learned that new communities need big shared memory, and it's for several reasons. One is it lets them scale things up from their laptops very transparently. That could be using programming languages they know and love, like Python and R and MATLAB. It can also be scaling up various applications that don't have very high scalability, for instance, genome sequence assembly. To make it accessible to this broad class of new users, we are really emphasizing about 5 or 6 things. The first of these is, oops, the advance took a while. The first of these is interactivity on slide 7. And interactivity is what we've seen in Exceed surveys as the #1 thing that people want to begin using HPC. They don't understand batch queues. They certainly don't want to wait for hours or days to try things out. And therefore, we are really prioritizing on Bridges ways of letting people do things interactively. In some cases, that's through virtualization, because many of these uses, people don't need full access to a node. They can get by with a core or virtual core and some fraction of memory. They also don't care about getting 100% of whatever they can get of CPU efficiency. What they need is perhaps something to happen right now. We also anticipate dedicating resources to projects that need it. And that in particular would be for gateways and for services that have to be up all the time. And for those you get reasonable turnaround and response times. On slide 8, gateways are a big part of Bridges also, and I think that's increasingly true across Exceed platforms. And the reason is that gateways provide a way for people who are not computational experts, who are domain experts instead, to really access HPC resources and to maintain data provenance, to orchestrate very complex sets of applications, and just make it all work together. We have a number of gateway partners with Bridges, and we've had others come along, that, like the Center for Causal Discovery at Pitt. On slide 9, I just want to mention briefly for this call, this is worth another call by itself. For virtualization on Bridges, we're offering it mainly to let people have flexible installations of software environments so they can have their own configurations of things like Apache and Tomcat and messaging and databases. For security, especially for NoSQL databases where there is not a mature security model, and to some extent for ease of use, and then for interoperability through containers. What we haven't seen demand for in Bridges so far is VMs for elasticity. And for that, of course, Exceed has Jetstream, and so I think those two form very nice complementary resources in that respect. And for elasticity, if you have Jetstream, for a lot of other things, they have Bridges that couples real HPC to some uses of virtualization. And we're using OpenStack to configure VMs, along with everything else. High productivity programming is really essential for Bridges. One thing that I find when I talk to new communities is they have code bases that are in languages like Java, R, MATLAB, Python. And increasingly, they're working other languages that are emerging, like Julia and Scala. And we need to support all of those as really first-class languages on Bridges to let people do what they need to do without changing their whole structure. And that's essential, and we're doing that. Spark, Hadoop, and that whole ecosystem are increasingly important. They've been important for a long time. They've not had a good match with HPC because a lot of people have equated big data with Hadoop on cloud-like resources, basically small, modestly provisioned nodes. But it turns out when you put up these environments on nodes that have a fair amount of memory, Bridges regular nodes have 128 gigabytes each, and you couple them with the Intel Omni-Path fabric that gives very, very high bandwidth, suddenly Spark becomes an even more powerful tool than it is the way people normally run it. We also see communities for developing frameworks that resemble Spark and Hadoop in that they are designed to bring together big data and big models, but in ways that are more efficient than the MapReduce paradigm or what you can get out of Spark or Hadoop. An example of that is Petrium of Carnegie Mellon. And so by being able to give people partitions to do Spark and Hadoop and other things that resemble those and letting them have those for an extended period, we expect to be able to enable not only those applications, but also applications that iterate between these models and traditional HPC, and let's call it large memory HPC, where we may have a large threaded code. And we have examples like that. Being able to do that iteration, especially if you can do it in a zero copy sense with one copy of data on the file system, really lets people start doing workflows on machine learning and other things that you just can't do anywhere else, including commercial clouds. Campus bridging, I don't want to talk about a lot on this call because our time is limited. It really consists of two things, though. One is federated identity management, so people can see their files at their campus and on bridges. I think of that as Google Drive for HPC, and a cloud-like burst offload capability. So the next slide is what Bridges looks like. This is an interactive tool that I showed at Supercomputing, and it's available on the TSC website. We can get the link out to anyone that wants it. It basically lets you see what portions of Bridges tend to be used for different types of application workloads. And so in your interactive version, this is clickable. You can click on every element. You can see what each component does, what it is, what's in it, what it's used for. And there's also, in that version, there's a panel that I've obscured here for legibility that lets you click on things like a gateway or Hadoop or large memory. And you can see which node types, which parts of the fabric become active, where the storage is. And so it's a great tool for letting people see how the machine will actually be used in practice. This diagram, though, gives a quick summary of what all the node types are. What's salient here is that Bridges is actually the first production deployment of the new Intel Omni-Path architecture fabric. And this is something we worked with for a long time. We partnered with Intel on ensuring that this particular topology, which we developed at PSC, will be routable and resilient to various types of failures. It's really a two-tier island topology. So at the top, we have these 6 orange spheres, and those are what we call the core network. Each one has 2 links between all of the other core switches. That's what provides us resilience and gives us multiple paths from each compute node to data. Below that, we have 20 of these yellow spheres. Those are the Intel, they're all just Omni-Path edge switches, but we call these leaf switches. Each one of those connects to 42 regular shared memory nodes at full bisection bandwidth. So that means we can do full bisection up to 1,176 cores. Each node has 28 cores. They're Haswell E5-2695 processors. And one can also do larger jobs spanning these, just not full bisection bandwidth. So parameter sweeps, things are not so tightly coupled, those can run broader. The large memory nodes are at the top. The 12 terabyte nodes are in orange. The 3 terabyte nodes are in purple. There are 4 of the 12 terabyte nodes, 42 of the 3 terabyte nodes. Down at the bottom in the regular nodes, we have 48 with 2 GPUs each, starting with 16 nodes with 2 K80s each, then introducing later, when they're available, as part of the technical upgrade, 32 nodes with 2 next-generation NVIDIA GPUs each. And all of the links here, the purple, orange, green, and blue, are all the Omni-Paths. The white structures at the top are the storage system. We call that pylon because the pylon is what holds up a bridge. That is something PSC has custom designed based on the data supercell and the data exascell. And so what we have here are 20 of what we call storage building blocks. Each offers 1/2 petabyte usable of highly high performance, high bandwidth, low latency, high reliability data storage. We aggregate those with Flash 2 and also with Lustre. So moving forward, since we're getting low on time, the node types are what I described verbally. 4 nodes with 12 terabytes. These are the new HP Enterprise Integrity Superdome X servers. They have a very nice internal fabric, very high bandwidth, very low latency, coherent shared memory space. We have 42 nodes with 3 terabytes. These give a nice spectrum of different use cases between very demanding shared memory to many modest things and things where I expect us to allocate on a more persistent basis. And then lots of these nodes with 128 gig each. Those are HPE Apollo 2000s. And that's where we'll have workflows, Hadoop, a lot of virtualization, a lot of interactivity, and a lot of capacity computing. As mentioned, these have the latest Intel CPUs. We'll start with Haswell. We will introduce Broadwell when available. And we'll have K80 and next generation GPUs. Bridges also includes dedicated nodes for doing databases and web servers. And this is important because a lot of people who are standing up services, both gateways and in new communities, want to have persistence. They want to have things that are always available. They want to have data that is accessible via RESTful web services. And that means having some elements that are always on, not just scheduled like a traditional machine. We also see an increasing move toward poly-storage systems, and not just using individual NoSQL and relational databases, but combining those in interesting ways. Bridges has really several forms of data storage. One is Pylon. That's the 10 petabyte central parallel file system. Each node also has local storage, and that is to support applications that want it. Things like Hadoop and NoSQL databases expect to shard data, but also to improve overall performance to Pylon and to improve performance consistency to Pylon. Basically, by keeping storage local, and I/O local that should be, it lets other people have higher performance to the shared storage. We have 10 petabytes usable to Pylon, about another 7 petabytes aggregate across all the nodes. So that's quite significant when you add it up. And that comes in for Hadoop-based applications, and that's Hadoop, Spark, and other things, and those will be accelerated by Omni-Path. I want to just say a quick word about Omni-Path since this is brand new to Exceed in the world. As I said, Bridges is the first deployment. We announced this at Supercomputing. We had announcements in the Intel booth and also in the HP Enterprise booth. The features of Omni-Path that matter to users are 100 gigabits line speed per port. So that's 25 gigabytes per second bidirectional bandwidth. And that's real. That's not before any, say, 64B, 66B encoding. That's realizable. It has a very, very high injection bandwidth of 160 million MPI messages per second. By having a 48-port switch, we got to develop the topology we saw in a few slides ago that lets reduce cost. It also lets us improve performance by having fewer hops in the network. There are a number of features Intel has picked up through acquisitions from Cray and QLogic for reliability, performance, and quality of service. And because Omni-Path implements things like InfiniBand verbs and the Open Fabric Alliance standard, we really expect that applications will run without modification. And that's critical to users. We've already talked about the topology. I won't talk about that now. As a very quick example of how a new style application is using Bridges, this is a portal for the Center for Causal Discovery. It's an NIH Big Data to Knowledge Center of Excellence that I'm a co-investigator of. And in this, we have a browser-based user interface. That's written using very common portable lightweight tools like JavaScript and HTML and CSS. That can run on the user's laptop or mobile device. That lets them prepare and upload data. It gives them guidance as to algorithms. It lets them run algorithms. Things that can be run locally, it runs locally. Things that either access large data or that need a lot more computational horsepower, It then sends over this red arrow that's come out of the internet to one of Bridges' web nodes. Right now, we've prototyped this on Data XSL. On that web node, they have Apache and Tomcat and messaging clients with typically Tomcat embedded in each of their web apps. That then interacts with database nodes for doing authentication, for metadata, and for provenance. It also interacts, the blue arrows are all Omni-Path. It also interacts by Omni-Path with Bridges' large memory nodes. And it's a large memory because these are large graph algorithms, and for what we expect people to actually do in practice, there's an advantage to having very large RAM. So that's where the real analytics happens, using algorithms like FastGES and other things. It's a package called Tetrad that's been evolving at Carnegie Mellon over the past 20 plus years. That interacts with the Pylon file systems, where there are large data sets for things like the Cancer Genome Atlas, functional MRI data for brain imaging, and other things. And so that all that happens on the back end. The user who has a client on their laptop or tablet doesn't have to know that they're harnessing Bridges or a supercomputer. They don't have to worry about all of this information flow and all of the applications on the back end. They just have to get their data up. They have to see results and be given tools to interact with and further refine those results. And that's an example. That's what we're seeing for other fields too, in humanities and social sciences. And I think that's going to be an increasingly important paradigm. The way I see it, it really gives us HPC software as a service. I think that's a big step forward to empowering many more users. So for getting started, as I said, we have starter allocations are available anytime, including now. People get ECSS support through those. Research allocations are open for the current period, and awards were made that will begin in January. We have an early user period that we will put as many people on as possible because we need that feedback, and they need to get work done. And for questions, please contact me anytime. The last slide is our target schedule, and we're pretty much on track with where we thought we would be. We still expect to have users on in January. The only real difference is that we will still be building out phase 1 in January. So we have targeted the amount of service units on the regular nodes to about half of what they would be in the future quarters. So we have about 20 million SUs for January to begin. And by the end of March, we expect to have all phase 1 up and running. Later in the summer, we will have phase 2 technical upgrade that will introduce additional large memory nodes based on Broadwell, and it will introduce the new next generation NVIDIA GPUs. We're leveraging these other resources you may know about, Greenfield and Data XSL, to help people get going. So I'll stop there and take any questions.
Nick, thanks very much. That was a tremendous talk. I'm glad we have it recorded for all the details that people will be able to listen to this later, and folks who weren't able to join today. Very thorough. Do we have any quick questions from folks on the call for Nick right now? Okay,
I'd like to add one thing, Nancy, that I forgot to put on this slide, and that is that we are planning to have our first Bridges workshop in March.
Oh, great. That sounds really good.
Yeah, we will invite all the Bridges users and people who are planning on using it, but it'll be open to everyone. I think that if anyone from ECSS would like additional information on Bridges, Sergio and his team would be happy to arrange something sooner, and we may look at ways of helping people understand the machine and look at different parts of it, like workflows or like gateways, and to help with people who may be helping users get going on the machines.
Right, yeah, that sounds good. That's what I was going to ask about with all the variety of kind of usage scenarios. how the Bridges team was preparing for that in terms of documentation, and also how ECSSers could get up to speed, and I think you've answered some of that. Carol Song, I think, has a question. Carol?
Hi, Nick. I have a quick question. So is it possible to run Docker containers on Bridges?
We absolutely plan to do that, yes. Is it possible today? No, because we're still bringing Bridges up.
But that's in your plan.
Yeah, there are so many people that need Docker. That's what we absolutely will do.
Okay, great. Yeah, we're interested in that, running, probably sending Docker instances from gateway. Yeah.
Right, we know we need Docker for you. We know we need it for genomics. We know we need it for humanities and library science people who are doing a lot with Jupyter-type notebooks in Docker. There's a lot of interesting work going on here. You and I, Carol, should talk. We should get together with J. Ray Scott and Sergio and make sure we understand how you want to use it, to make sure we understand how everyone needs to use this, because there's a lot of variety.
Yeah, since you mentioned March, are you going to run the workshop there in Pittsburgh?
Well, we're going to do like we do all of our training for Exceed. We will originate in Pittsburgh. We will make it open to a number of remote sites with full bidirectional HD video and audio. Typically, we have up to about 15 other sites.
Okay.
So
yeah, I just thought maybe that time that would be a good time to have some further discussion.
Carol, hopefully we can do something earlier because the March workshop will be kind of for users. But I think in terms of, getting things going, I think we should probably talk as soon as possible.
I see. Okay.
The other thing is, if the March workshop is very popular and we can't accommodate all of the sites or all the users, it's easy to do another one.
Hi. Sorry.
No, I'm sorry. Go on.
This is Mona. So I have a couple of one comment and one question. I have also two collaborators who are also very interested in Docker, and so I would like to join this group that you guys are going to be discussing Docker sort of future plans. And in terms of your scheduling for Dockers, is that going to be phase 1 or phase 2?
So I consider all the, thanks for the question, Mona. That's actually a really good one. So I think we need all of the software environment. Well, let me be careful here. Docker's phase 1. I'm sure that we will evolve some things on the system over time, but I think Docker is one of the things we need to have very early on. Phase 2 is purely a hardware upgrade. It introduces some new technologies that, based on the solicitation, when we had to have the system done, we thought were worth intersecting. And so that's why phase 2 exists. But I think all of the software functionality we mean to have available as soon as possible in phase 1. I think we need Docker quite early in that process. Sergio, I think what we're hearing, and we should have thought this before, is we should probably just set up basically a little Docker, let's call it a task force or working group for Bridges.
Yep.
And maybe just set up a remote meeting where we can start capturing requirements and making sure all this is addressed.
Well, I can start a doodle poll. Maybe, I don't know if we can still do it this year, but maybe for early January.
Yeah, let's also think about setting up like a Docker. Let's talk to our groups. Let's talk to our groups of PSC about what we could do as basically a web-based thing. We're failing that, a mailing list.
Yep.
Yeah, please add me to that list. This is Mona Wong at SDSC.
Yep.
Yeah, I'd rather have. I'd rather have it be something a little bit more easier to deal with, like a web-based service, than a mailing list, because we already all have too much mail. But let's see what we can do.
Yep.
I also have another question. So you mentioned that Bridges is intended for sort of non-traditional science research with big data. I have a possible collaborator that I don't think their data is big, but they're definitely non-traditional. Is that also a possibility for them to use Bridges?
Well, again, a fantastic question. One thing that I've found in dealing with new communities is exactly that. And as we speak, I'm in fact also writing a blog, a PSC blog about this. And I think there are two ways to think about data. There's big data in the sense that people at XLDB and the media talk about big data. There's internet scale data. But I think what's more important is what I call relevant data. And to me, relevant data is data that is too big to deal with on their workstations or laptops. And I think that's the threshold using Bridges. And so I don't care if it's 100 gigabytes. If you can't get through it because your laptop bandwidth is 100 megabytes a second, you can't pour through 100 gigabytes, I think that's absolutely fair game. We don't have to be many terabytes or petabytes to gain value from research.
Okay, great. Thank you.
Okay, I'm glad this has been such an active topic of discussion. Lots of interest for you, Nick. If you do establish some working groups, you might want to send a note to ECSS all just to catch people who didn't happen to be on the call. But send me your slides when you have a chance. I don't think I can grab them from this webinar. And then Nick's slides will be up on the Symposium website as well as his contact information so folks can follow up afterwards. So thank you very much for a fine talk. Go ahead, Nick.
I just want to thank people for the questions. These symposia are great because they catalyze good ideas.
Yep, absolutely. Thanks for putting the presentation together. Now I'd like to introduce our second speaker, Pragnesh Patel from NICS. So Pragnesh is going to describe to us his work with PI Joshua New from Oak Ridge. And it's really kind of interesting work because it's looking at energy efficiency in buildings. And so you're modeling not only individual buildings, but then also looking statistically at multiple buildings and how you do that and implementing machine learning packages and statistics in R, and so a lot of kind of novel types of computing approaches from an ECSS perspective. So Pragnesh, I believe that you have control and can advance the slides, and so we'll let you go ahead and take it away. Thank you.
Thank you. So, hi, this is Pragnesh. Today I'm going to talk about one of my ECSS project, which is design of experiments and big data analytics for energy efficient buildings. So before I dive into it, let's go through the background of this project. So basically this project started in Oak Ridge National Lab, and there is a building technology research center here. They are using Energy Plus to simulate the buildings and try to figuring it out which are the most useful parameters to make a building more energy efficient. Then I will talk about simulation and experimental design, and then the statistical techniques which we developed using R and some of the packages for sensitivity analysis. I also have some analysis results, and recently we also integrated this pipeline into workflow system called openDIEL, which is developed by Kwai at NICS, and I think he's also on the call. So building in United States, basically 40% of primary energy based on carbon and 73% electricity and 34% based on gas. As you see here in building in China and India, basically they are expecting by 2013 60% of urban building floor and 67% of all buildings are yet to be built. So global energy consumption will increase 50% by 2030. Now, let me describe more about which are the goals for ECSS project. The first goal was to port Energy Plus simulation code on Excel resources. Then after integrating the Energy Plus and other pipelines into openDIEL workflow system, and which will allow to manage and run multiple instances of Energy Plus simulation code, implementation of experimental design framework, and this will basically help to reduce the number of simulation to be run. And then after the implementation of sensitivity analysis tools, so once we have the data from the simulation, we need to know which are the important parameters to make the building more energy efficient. There are total 16 different kinds of building types and 16 climate zones all over the United States. And also the fast portable workflow solution that leverages workflow mechanism. So Energy Plus is it's a simulation program. You can find more information about this program on energyplus.net. It has many inbuilt functionality for dynamic simulation. It has also inbuilt features for different climate zones, as well as it provides the configuration file for different kinds of buildings such as hospital, retail, small size businesses, medium size businesses, residents, and so on. Currently, it has been transitioning to C code. Originally, it was written in Fortran, and it also once this Energy Plus simulation runs, it provides the detailed outputs with selected time resolution. It could be hourly, it could be monthly, weekly, or yearly. And as far as the input is concerned, it has the standard input file which describes the building, and this input file is about 300 lines of code. Domain experts, they know their parameters and they pick most useful parameters for different kinds of buildings and also based on the climate zone. The most useful group consisted about 156 parameters, and basically what we wanted to know is, like, if we turn on one knob and turn off the another knob, which are going to be the optimal parameter settings for given constraint. And this resulted basically in the gigabytes of data for one building type and one climate zone. So let's take an example of just a retail as a building type and one climate zone such as Atlanta. Our motivation, this is basically PI's motivation is to run the parametric analysis using the Energy Plus as well as some kind of parametric tool, and then do the uncertainty quantification. One is based on the building envelopes, which is like they also have developed the prototype buildings in Oak Ridge, which has the sensors and it collecting the data from the sensor, and then comparing the output from the Energy Plus simulation to that sensor data. And the second one is just running the simulation code and then apply the sensitivity analysis algorithms on simulation data. And as I mentioned, there are 16 different building types and 16 types of climate zones for this project. So here is an example. So let's say domain expert, he selected the input parameters for Energy Plus simulation code, and then he feeds into the Energy Plus code and then run the simulation, and then try to compare that result with the sensor data. Most of that first time it never could be correct, and he has to run this simulation many times to match the results with the sensor data. What PI had in mind was basically creating something like the easy button. So you start with the basic configuration and then run the multiple simulation of Energy Plus, and then try to compare those results with the sensor data. And this could be like the iterative process. So once we learn more and more about simulation data output and comparing with the sensor data, it's going to be more and more intelligent. So first experimental setup was with the Zebra Alliance homes and Markov order design. This is basically a 2,800 square feet research home in Oak Ridge. Basically, some of this home has energy efficient technologies such as standing steam, seam metal roof, Energy Star appliances, high efficiency water to water heat pump, and energy recovery ventilator, structure insulated panels, and so on. Now, there were three main sampling methods used to vary the input parameters. First one was the brute force with 156 building input parameters were selected, and these were about 12,000 Energy Plus simulation and generated about 143 gigabytes of data. Second one was Markov order 1 with all 156 parameters were kept at their default value while iterating through each parameter to set its extremes. And this data set contained 299 simulations and 3.9 gigabytes of data generated. And third one was Markov order 2 with all 156 choose 2 pairing were run in all possible mean max configuration. And this data set contains approximately 28,000 simulations and approximately 450 gigabytes of data. Experimental setup 2 was about designing the fractional factorial. So in statistics, design of experiment, input parameter of multivariate function under study are called factors, and output parameters are called responses. The objective of design experiment is to measure the effect size of factors and their interaction on the response through an additive decomposition of the multivariate response function. And as you see, like the fractional design expression was L to the power k minus p, where L was a number of factors and k number of factors investigated, and p was size of fractional of full factorial used. And actually, we use the regular design power 2. Two-level fractional factorial designs generally are popular, where k factor at 2 level each. There are 2 to the power k possible factor combination. Fractional factorial designs allows the use of small fractions of this large number by carefully controlling the pattern of factors. And for this fractional factorial design, we use the package from our language, which called FRF2 package. This package was very helpful to figuring it out the best possible combination for the simulation to be run. And we also work with the author of this package to optimize for this particular problem size. And this package basically written in R, and there are some code which is also written in C underneath. So here, as you see in this table, basically it's 20 inputs and ranges sampled to generate 1024 simulation. It has like the default mean value and the max value. So these are the input settings we use to generate the 1024 simulation. Now, once we generated the data for the simulation to run, it generated 1024 CSV file, because that's the default format from Energy Plus. So here I'm just talking about one particular building type and one particular climate zone. Basically, the goal is to generate the data for all different kinds of climate zones as well as building types. So then after, once we have the data from the Energy Plus, what we need to do is basically the sensitivity analysis. We wanted to know the interaction between different parameters and which are the most useful parameters for buildings to save the energy. And for that, we use the analysis of variance, and basically we feed the multivariate analysis of variance model, treating the month as a repeated measure and with 20 factors and two-way interaction, which fits to the 1024 observation. And still we had 778 degrees of freedom left for the error term. And I'm going to show you the result in next few slides. Basically, these are the multivariate PLI statistics gives strong significance to all factors with the exception of few parameters, which I will show you in the plot. And basically, here is the results, which shows that the coefficient over 1,000 kilowatt hour energy for the electricity in 1 month. So basically, as you see here, one would expect a higher thermostat settings on SCCL6, which is the cooling, reduces the electricity use. Generally we get more reduction in summer than in the winter. And the next slide. This is also the factor with the largest effect on the electric use. And similar, we get the interaction plot for gas as well, and gas is used only for heating only. And basically this also reflected in the fact that all main effects are positive, meaning that the higher thermostat setting leads to higher energy use. And here are the basically this provides the visualization effects across the month of year. And as we seen in the previous 4 plots, some factors have an effect that is 1 or more order of magnitude larger than the rest. And as a result, we only provide the plots for factors where there is a visual difference between the 2 settings. So here all are the plots for electricity and gas. These are the variables which are most useful based on our sensitivity analysis. So basically, the conclusion, we use the sampling 456 parameters for residential building, which is basically a naive approach without doing any special design of experiments. What we figured out, we started with that, and Pia and his team generated about 470 terabytes of data. But then we decided it's better to start with the design of experiments, and then we developed the design of experiments techniques. We first applied with the standalone retail only, and also did the sensitivity analysis. And these results match with some of the publication before, and we also consult domain experts, and they also agree with our results. So looks like this is going to be a better technique rather than applying the naive techniques to run the Energy Plus simulation code. Right now, we are working on parallelizing the analysis modules using the PBDR package, which basically provides some of the useful parallel techniques such as parallel linear modeling. It also supports the MPI functionality and some of the metrics multiplications, such as the package called PBDDMAT. And we are also working on the in situ analysis, and the idea is basically once it generates the data, we need to do the local analysis first on each node, and then after we will merge those results and do the global analysis. Right now what we do is generates the data on different nodes, combine those data into one node and just run the analysis script on one node. So now let's talk about the workflow system which we use for this particular project. This is basically the openDIEL. openDIEL, it's a workflow system which aims to allow the communication between loosely coupled codes. And in this particular case, we use the Energy Plus as a simulation code, and also there are some scripts which we use for processing the data before we feed into the actual analysis code. And we also integrated the plotting code into it. So basically openDIEL combines Energy Plus as well as some pre-processing scripts, analysis code, and plotting code. openDIEL, it communicates to the tuple server, and it also has the method. It has two different communication methods. One is basically the direct communication, another is for indirect, which is kind of cloud style communication using the tuple spaces. And here is the organization of openDIEL. So basically openDIEL, it has the driver configuration file, which is basically written by the user. It has the executive library, which is basically useful for scheduling and managing the workflow of a set of tasks prescribed in the configuration file. So as you see here, core libraries, executive libraries, and communication library, those are like the main component of openDIEL, and users should not worry about those modules. And then user has this configuration files, user code, as well as the modules. So basically, as I mentioned, it has two different kinds of communication libraries. One direct communication, which is wrapped around the MPI to communicate the large chunk of data, and it provides the non-blocking and blocking functions such as IEL send and IEL receive. It also has the get and put to send the data and get the data from the other function. And it's basically movement parameters specify the point-to-point transfer. Here is the direct communication code. As you see here, it sends the data to the processor using MPI send, and then in the IEL communication code, you basically exchange the data with process using IEL move, and then you receive the data from another processor in MPI communication code. And here is basically the schematic diagram of how two processes communicate with each other in the direct communication. So as I mentioned before, we integrated openDIEL, Energy Plus, and some other codes into as a one package, and we have configured to run on Darter and Wrangler. So right now this whole package can be run on Darter and Wrangler. And here is the diagram about how the Energy Plus and other components run within the openDIEL, and then as you see here, only processor 0 runs the analysis code, but in future we plan to run the multiple R code on different nodes, so that way it's going to be much more faster. But right now the problem we are facing, it's about how to parallelize a particular multivariate analysis algorithm, because we try to parallelize it but we don't get the result what we expected. And this is the configuration file. In the workflow, you specify the group, and here here I specify EP7, which is Energy Plus 7 version with read var, and you specify the order, which should be the first and which should be the next one. First, I want to run the Energy Plus 7, and then run the read var, which is the processing script for simulation data. Once it generates the CSV file, I process those data in particular format so I can feed into the R analysis code. And for openDIEL, we are still working on it and implementing some more functionality into it, such as tuple server control module, which is going to be helpful to figuring out the dependencies and dynamic scheduling. Mode maker, which is for easy installation for the user. We also work on the tuple server scaling, which is going to be useful for scaling openDIEL workflow system on thousands of core. And we also started working on the openDIEL GUI, and this is going to be helpful for the user who may not have enough experience with HPC resources. So these are the features right now we are adding into the openDIEL framework. And I think that's all from me. I like to thank PI and his team. Thank you.
Pragnesh, thank you very much for a good talk. Do we have any questions for folks on the webinar for Pragnesh? I have just a couple quick ones since we're out of time. I was going to ask about what systems you are running on, and then you mentioned it at the end, Darter and Wrangler. This is a nice, unique use case for Wrangler. I haven't heard about too many applications making use of Wrangler yet, so it was really interesting to hear about this one, especially from the data aspects. Sorry, go ahead. I didn't know if somebody was jumping in there. openDIEL also sounds like a really interesting workflow package. It sounds very generalizable, like it could be used for other applications besides this one.
That's true. Yeah.
And so I was going to ask if you wouldn't mind following up with Marlon Pierce afterwards. You might know that Marlon leads this workflow initiative. Yes. And it would be really interesting to kind of fold this into some of the other workflow activities that are going on, especially with the move towards the GUI and some of the new systems that are coming online, and kind of a generalizable use of openDIEL might be really quite interesting.
So yeah, I think Kwai is on the call. He's a PI on that project. Basically, he started developing this workflow system for multi-physics code, and he has shown that with many applications, it's really helpful for running this system as the package. And then when he started working on with us on this particular project, he suggested us to also integrate Energy Plus into openDIEL. And I think basically he has started working making the configuration file for the different system as well. So many users can use the same configuration file on the different system on Exit resources.
Yeah, perhaps I can comment a little bit. This is Kwai. So if you want to run a whole bunch of serial calls on the parallel system, you don't have to do anything at all. All you need is the executable of the serial call. And then in input file, just tell where the executable is. And then it will run it for you. And as many groups as you like, as many iterations as you like. So there's no explicit work or additional work using it. And these are simple wrappers that are portable on all the system because they're written using C. So they have been ported to Wrangler, Stampy, and Comet, and Darter. So in terms of portability, for running a whole bunch of serial code, it's just straightforward.
How does it handle getting a selection of processors to run on? Because it probably doesn't go one by one submitting jobs through the batch queue.
Right. The configuration file as tell you which directory you want to run it. So it will find it out from the directory and how many copy of the code you want to run it. For example, you want to run to ./energy plus. That's typically you run it serially. And then you tell them that, okay, I want to run 5 copy. And then that's just 5 copy. That's it. And it will run it on energy plus 0 directory all the way to 4th directory. And then you can concatenate the data using a script, a Perl script, or our scripts, whatever you like, in the second groups of execution.
Okay, thanks, Kwai. Very interesting. Any other questions for Kwai, Pragnesh? Thank you very much. Their slides will also be up on the website with contact information for Pragnesh if you'd like to get in touch with him afterwards. So I'd like to thank both of our speakers for making this another interesting ECSS symposium. Thanks very much, Nick and Pragnesh, and thanks to everyone for joining.